Okay. Now we can start the course itself. Before that, whatever I said, it was more like an introduction about how are we going to follow the course and what do I expect from you. But what is actually vibration? Well, specifically, we are going to study mechanical vibration, right? But what is vibration? So the way I look at vibration is I look at it as applied dynamics. What do I mean by applied dynamics? Remember, in dynamics, what we were doing is that pretty much you were using Newton's laws to find the relationship between the force and the acceleration, right? F equals ma, and we were just putting together the equations of free body diagrams and kinetic diagrams, and they were trying to find out what is the relationship between a force, given force, for any given force, and the acceleration that mass or the system is going to have if we apply that force, or how much force we need to get to a specific acceleration, right? That was pretty much the general idea in dynamics. Now, in vibrations, what we do is that we want to actually go further. We want to solve those equations. We want to know, well, this is the relationship between the force and the acceleration. How can we find the relationship between the force and velocity? How can we find the relationship between the force and displacement? Right? Where does this system go if we apply this much force for this period of time? Right? Well, obviously, we're not talking about every single type of systems we talked in dynamics. It was more broad. In vibrations, we're going to be focused on vibrating systems, as the name says. And what is a vibrating system? Well, the way I'm going to define it is, as a general definition, is that any motion that repeats itself after, or let's put it this way, after an interval of time. Right? So let's say we have some specific motion. We're looking at the motion. If that motion repeats itself after an interval of time, that is vibration. That is oscillation. That system is vibrating. That system is oscillating. Right? A very good example is in my back. I have a pendulum here. This is just a mass connected to support by string. Right? If I just let it go, right, it vibrates. This is vibration. Right? This is a motion that repeats itself after an interval of time. And we'll talk about what that interval of time is and how do we define it. It actually has this it's important for in theory of vibration and the way we look at things. But for now, just take it as a general definition of vibration. Now, there is this actually quote, before I say the quote, where do we see vibrations is pretty, I would say, interesting, at least to me, that daily life, you see vibrations pretty much everywhere. You see vibration, you see oscillation everywhere. There is this quote from Einstein that says, everything in life is vibration. Now, this is a pretty significant or bold statement, but actually it is true. So everything in life is vibration, as he said it. Now, a couple of examples I can give you is, think about any repetitive motion, any repetitive thing that happens around you, right? Or within you, actually, right? Start with breathing. Right? The idea of breathing, what do we do? It's a repetitive motion, right? It's a motion that repeats itself, following the definition, after an interval of time. You breathe in, right? You breathe out. Breathe in, breathe out. So you get the oxygen or the air in, get the air out. It's a repetitive motion. So it is type of vibration. It's an oscillation. The other example is walking. Right? When you're walking, well, you're just pretty much doing the same thing over and over. Your legs are following a repetitive motion. More I would say, technical examples or things that, well, let's go with heartbeat. Actually, your heart beats, right? It's a repetitive motion. After a specific certain time interval, it just repeats itself. So it is just an oscillation. It's a vibration. To be more technical or give examples about something that we might know less is human speech. Human speech is a vibration. Why it is a vibration? Well, think about it. When we talk, the whole thing happens because there is, I can actually, so when we talk, the whole thing happens because what we do is that we create a pressure wave in the air. When we talk, bunch of, to put it in a simple way, bunch of air molecules start vibrating, and because of their vibration, they transfer this vibration to molecules next to them, and they transfer them to the molecules next to those molecules. So we create a wave in the air that propagates. So that's the idea of human speech, and deep down, it's just a vibration in air molecules that creates a pressure wave. Now, go to the other side. The reason we hear is vibration. Why? Well, the same air pressure, air wave that we generated when we are talking, when it reaches our ears, like eardrums vibrate. When those molecules get to our eardrums, that vibration is transferred to our eardrums, and our eardrums start oscillating, and our brain interprets that oscillation as words. So it's pretty much a vibration. Now, there are like other examples. Even seeing is a kind of vibration. If you go deep, light waves are pretty much, it can be considered as kind of an oscillation. But if we want to, generally speaking, if we want to classify, well, these are, I talked about vibrations, but another specific example is actually, I forgot to mention, is music, right? The same reason that human speech is vibration, music is vibration. It's actually more obvious. If you pluck a guitar's string, right, it starts vibrating, and then that vibrating string creates a wave that is the music we hear. So it's pretty much even any kind of musical instrument that you use, even a whistle, right? You're blowing, again, you're creating a wave, you're creating a vibration. That vibration, the way the shape of the flute or a whistle is, the way you whistle determines the type of sound, because the type of vibration changes in that system. Now, this is general definition of vibration, but we are going to be mainly focused on mechanical vibrations, obviously. If you want to define or classify vibration, there is this general way of looking at vibrations, that we can say a vibration can be good vibration or bad vibration. Now, it's a very rough, raw way of defining vibrations, but let's start with bad vibration, because I think that's more obvious, and it's generally the most obvious case, or these are the most obvious cases when we talk about bad vibrations. Examples of bad vibrations are, the very common one is the car vibration, right? When you're driving, you're passing a bump in the road, your car starts vibrating, right? You feel that whatever uneven surface you just passed, which is not a good vibration. That's why we designed the whole suspension system, how to get rid of or how to isolate that vibration from the passenger in the car, right? We want to make sure that even if we pass a bump, the person sitting in the car feels the minimum disturbance, right? We want to provide a comfortable ride for the passenger. So that's kind of bad vibration we're trying to get rid of. Noise. Also, you have air conditioning in your house, and you turn it on, it starts making this weird noise. for whatever reason, the installation problem or something else, it creates noise. That's a bad vibration. As I said, sound is a kind of vibration. Or there is some construction site next to your apartment, which is pretty common in Manhattan. I'm going to warn you, sometimes during the semester you might hear some construction noise here. But yeah, construction noise is a kind of vibration. It's a bad vibration. You don't want it. You try to equip your apartment or your house with different materials to minimize the amount of noise that gets into your house from outside. So that's another example of bad vibration. Earthquake is a kind of vibration that we don't like. Big earthquakes happen. What we want is, well, we want buildings that are capable of handling that much of vibration, that amount of vibration. So we design systems, buildings in a way that can handle the vibration, or they can isolate the ground vibration from the motion of the building, so people living in the building feel less, and the building itself can handle that much sudden random motion. So that's also a bad vibration. That another example is turbines. It happens a lot, especially in mechanical engineering. That's one of the interesting fields that people look into. That when we have turbines, what happens that any kind of rotating system, we'll talk about it a little bit later on during the semester, more towards the end, that when we have a rotating system, if that rotating shaft is not symmetric exactly, the mass distributed in a shaft is not symmetric, right? Let's say in this corner we have more mass than this corner, which can happen. It's a manufacturing problem. There is no guarantee that they make a shaft that is perfectly symmetric with respect to the axis, like it's axis symmetric. That creates actually vibration. And there is this whole science of balancing, shaft balancing, and it's actually a profession. People do go to power plants and they try to balance the shafts of turbines. This is a bad vibration. We're trying to get rid of it because it reduces the efficiency of the system. It creates noise that we don't want. So we try to get rid of it. Also, examples of bad vibrations I could think about. A good vibration, there are good vibrations, in case you were wondering. The actually relative example to earthquake is seismometers, like seismographs. I don't know if you've seen them, the old-fashioned ones. There is a needle that goes up and down. If there's an earthquake, it gives you a record of the ground's motion, so we can see how much the ground moved during some specific earthquake, right? Depending on where that measurement system is, that seismograph is. So it's a good vibration. It helps us to understand what is happening. What else? We have, my personal interest is energy harvesting. There is this new field in vibration that you can actually harness the energy of a vibrating system. Right now you see it actually in cars, generative braking systems. What happens is that you can actually, they use the motion of the tire to generate electricity and take it back to charge the batteries, especially in electric cars. So there is this whole science of how can we actually use this vibration and take it and convert it to electricity and use that to charge batteries. So that's a good, it's not a good vibration, but it's an application of how to use vibration for a good, I would say for a good purpose. The other thing is in musical instruments, right? As I said, we enjoy music. If there is no vibration, there will be no music. Imagine that, right? So we need vibration. It's a good vibration. You want to listen to guitar, you want to listen to flute, you want to listen to different types of instruments, drums, right? You need vibration. So it's good vibration. Or from their speakers, right? The way the speakers, think about it, how do speakers generate sound? Right? If you've seen a speaker when it's working, it's functioning, the signal goes from computer to speaker and the speaker vibrates. The center is like a series of magnets, electronic circuit, and that vibration creates sounds. It's good vibration, right? If we didn't have them, we couldn't actually use we couldn't have speakers. So it's good vibration. It's a good application of vibration, or application of vibration for a good purpose. Now, just to wrap up, I'm going to talk briefly about the history of vibration and where did the whole thing start. This is a course about mechanical vibrations. We are going to talk about the theory of vibration. So we need to know a little bit about the history. If we actually want to think about the history of vibration, we have to go all the way back to, I would say, as long as probably 4000 BC, when the Indians, Hindus, Chinese, Japanese, Egyptians, they were creating and playing around with musical instruments like old drums, the initial versions of drums or whistles. These were the outcomes of human beings experimenting with vibration and trying to figure out how does that work, right? Obviously, at that time, there was zero understanding of the theory and what's going on behind the scene, but they were still using vibration to create music. Then fast forward, come to Greece in 5th century BC. I believe, I think it was 5th century BC, Pythagoras was the first person who actually started looking into this. There is a story that he was passing by a metalworking shop, and he heard that different sounds are coming out of different hammers. Like workers were using hammers to hammer metals, and he realized that the sound coming from each hammer is different. So first he thought it's because of the worker using it and the way he's hammering the metal. So he went there, he asked them to switch their hammers. What happened was he realized that actually the sound coming from a hammer is still the same. Doesn't matter how they use that hammer, how hard they hit the metal with that hammer, the sound is the same. So that was kind of a step, or the initial notion, or the first thing that made him curious about what is the science of this, how does this work. So what he did is that he went home, he basically put together a series of experiments. So the famous one that we know of is he pretty much put a string. Let me see if I can put it here. He put a string and pretty simple tool. He used a piece of wood, right, something like this, and he attached the string to one end and pass it through here, attach it to another, or pass it through this edge, put a weight there, right, and then put a bridge, wooden bridge here. Now, and he did a series of experiments. This is just a piece of wood sitting, let's say, on a surface. He did a series of experiments, actually. He changed the amount of this weight to see how does that affect the sound coming out of this string. He moved this wedge, like wooden bridge, around, back and forth, to figure out how does that affect the sound coming from this string. And he realized that the sound is changing. Well, we know it now. But back then, that was something interesting. And the unfortunate thing is that there is not really that much notes left from his work. So whatever we know about his work is mainly because of his students, whatever was left from his students, or anecdotals, like some stories about what he did or experiments he performed. Now, there is another thing, again, around that era, 400 BC, that there is this text left from one of students in the school of Aristotle, that he wrote somewhere in one of his texts that that piece of text tells us that they had a good understanding of vibration, or to some degree, that he wrote that there is a relationship between vibration and sound, and when in every object that is vibrating or it's moving, it creates sounds. An example of it was guitar string, right? String guitar or whatever musical instrument they had that had a string. So this is what he wrote back then. So it shows that they started getting some ideas about how things work. But if you want to talk about the actual theory and what we actually follow nowadays, we have to move forward all the way to, I think, 16th century during Galileo. Galileo is pretty much famous to be the father of experimental science. So there is this story again, and a lot of these stories we can't actually verify how truthful they are and how true they are. These are stories might have been added to the history to just make it, to give it some spice, I guess. But there is a story that he was sitting in a church one day. He was listening to a sermon. He was a little bored. He was looking at the ceiling. He saw these chandeliers swinging, and because of the wind blowing from some open window. Now, what he did, he just got curious. He started. He used his own heartbeat to measure how long does it take for these chandeliers to go from one side to another and go back to where they initiated their motion, like similar to this pendulum I have here. Think about it as a chandelier. How long does it take when I let it go? How long does it take to go to the other side and come back to where it started? Right? This is a cycle. We call it a cycle. And from where we started to go to the other side and come back to the initial position. It's a cycle. So how long does it take to finish a cycle? Which we call this time period, the period of motion. Later on, we'll see when I officially define that. So he got curious and he started measuring. He realized that doesn't matter how hard the wind blows, that time is constant. Time period is constant. Time to complete the cycle is constant. Doesn't matter if, let's say, if this is, I let this go from here, let me move it a little bit. Doesn't matter if I let it go from here, right? Or if I let it go from here, farther from its position, called the first position that this pendulum is standing, equilibrium position. That's the position that this pendulum or the system is in equilibrium. Right? It's not moving, it's fixed. Now, the time that takes to finish one cycle, he realized that it's actually the same, which was interesting. Doesn't matter how hard it's pushed or how far we let it go from the equilibrium position. This is the equilibrium position, right, at the beginning. The time period is constant. What else he realized? He also realized that no matter how heavy the chandelier is, some of them are heavier, some of them are lighter, still the time is the same. As long as the string or the cable, or I guess back then the chain used to connect this chandelier to the ceiling, the length of those chains are the same. It doesn't matter how heavy the chandelier is or how far we let it go from the initial position. The time period is constant. If it takes 1 second for this to go to finish one cycle, it's the same for all these chandeliers, as long as the length of the chain is equal. So that was an interesting observation, and that's where actually we start. Of course, we're going to pick it up where in that position we start looking into pendulum's motion. I will see why does that happen. Why does the time period is constant, mathematically speaking. That was, I would say, the most important observation. And then again, moving forward, 17th century, I believe people like Newton, Taylor, you've heard these names, Hooke, Robert Hooke. We're going to talk about Hooke's law when we talk about springs. These mainly mathematicians contributed to the science of vibration, the theory of vibration. And then 18th century, again, more mathematicians. Mainly these people were mathematicians back then, because a lot of these contributions are coming actually from mathematicians. You'll see vibrations. We deal with math very frequently with different concepts that you've learned from before. In 18th century, I think people like Euler, and you've heard these names, Fourier, if you've dealt with Fourier transform before, Lagrange, these people contributed to the theory of vibration, and they just put more pieces together to make it more complete. How can we actually study more complicated systems, and how can we use different methods? For instance, we're going to see Lagrange, a Lagrange method I explained when I was talking about the syllabus. There's a Lagrange method, which is totally different from Newton's method. We have 3 laws, Newton's laws, and we use those to derive the equation of motion, which is basically the relationship between the force and the acceleration. Now, Lagrange showed up and said, you know what? I'm going to look at the systems in a very different way. I'm going to look at the systems using energy, right? Potential energy and kinetic energy, and how do they convert? And then he derived, or we can derive the equation of motion, or that relationship between force and acceleration, using Lagrange method, which has nothing to do with free body diagram or anything that we do with when we are using Newton's method. Hopefully we'll talk about that a little bit, at least, so you get a taste of how it works. So what we do in next class is we're going to start from the pendulum. Right? We're going to start from a simple pendulum, and we'll see how can we derive the equations of motions from there. I will start introducing a couple of concepts like time period, natural frequency. How do they how do we define those, which are very important concepts in mechanical vibrations, and they help us to understand the systems and the way they work. So I'm just going to stop here. It's almost 9. And then we'll just pick it up from here. We'll look at the simple pendulum. You have seen the dynamics of it before, so it's pretty straightforward. We derive the equation, then we solve the equation of motion for a simple pendulum, and we define a couple of things from there, and we take it from there. Okay, any question, folks? Today was more just about the history and introduction. So what I'm going to do is that I'm also going to upload a paper on the history of theory of vibration. It's a pretty good paper, relatively old, but doesn't matter because it's talking about the history starting from 4000 BC. So if you're interested to know more, I just gave you a very brief review of what happened in the past, and how did that contribute to the theory of vibration that we have today to some degree. And we'll see more about these during the semester. But if you're interested, take a look at that paper. I'll upload that paper on Moodle under the same section. So what I'm going to do is that, let me stop the recording.